Lucchini Mame Forge represents a benchmark in modern forging technology, integrating a full-cycle steel mill with advanced mechanical processing capabilities. Central to its operations are two high-capacity forging presses rated at 3,200 and 6,000 tons, enabling the production of large, high-strength components with consistent metallurgical integrity. The facility is equipped with state-of-the-art heat treatment systems to ensure optimized mechanical properties and structural uniformity across a wide range of steel grades. Precision machining operations are performed using advanced CNC equipment, ensuring tight tolerances and surface finishes that meet stringent industry standards. Each stage of production is monitored for quality, ensuring performance and reliability in critical applications. The integrated warehouse allows for efficient logistics and inventory management, supporting prompt global shipments. The BOAST AR90 is a high-performance machine used for rough milling of crankshafts in the automotive and manufacturing industries. The process typically begins with the selection of the raw crankshaft material, which is secured onto the machine's workpiece fixture. The BOAST AR90 uses a robust milling system to remove excess material from the crankshaft, shaping it according to the specified design dimensions. During the rough milling stage, the primary goal is to achieve the necessary rough shape of the crankshaft, typically involving the removal of large amounts of material. The machine employs high-torque spindles and advanced cutting tools that are specifically designed for heavy-duty material removal. The cutting tools are programmed to operate with high precision, ensuring that the material is removed efficiently while maintaining the integrity of the crankshaft's structural components. The BOAST AR90 also features an advanced control system that monitors the milling process in real time. This system adjusts feed rates, cutting speeds, and tool paths to ensure optimal material removal without overloading the machine or tools. Additionally, the system helps in managing heat generation and vibration, which can negatively impact the milling process. This rough milling process is critical in preparing the crankshaft for subsequent machining steps, such as fine milling, grinding, and finishing. By effectively removing large sections of material quickly and accurately, the BOAST AR90 ensures that the crankshaft is ready for precise final machining, meeting the necessary tolerances and specifications for high-performance engine components. Ultimately, the BOAST AR90's capability to handle heavy-duty rough milling while maintaining high precision contributes significantly to reducing overall production time and improving the quality of finished crankshafts. The Danobat VTC8000 is a vertical turning center specifically engineered for the precision machining of large, heavy components such as wind turbine hubs, aerospace parts, and large diameter bearings. It offers a maximum turning diameter of up to 8,000 millimeters and is designed to handle workpieces weighing several tens of tons. The machine structure features a robust, double-column design that ensures thermal stability and vibration damping, enhancing machining accuracy and surface finish. Equipped with high-torque main spindles and heavy-duty hydrostatic guideways, The VTC8000 delivers optimal performance during roughing and finishing operations. Integrated tool changers, optional live tooling, and in-process measurement systems enable multitasking capabilities and reduced downtime. The control system, typically a Siemens or Fanuc CNC, allows for advanced programming and monitoring. The Danobat VTC8000 is ideal for manufacturers requiring high precision, large-scale vertical turning with consistent repeatability and productivity. Corot QD is a grooving system engineered to enhance machining performance and reduce material waste by using small-width inserts. It is particularly suited for low-alloy steels, with various tool and insert combinations available. For example, with a 3mm 0.12 inches insert and tool setup QD25 paired with QD1125, cutting speeds reach 140 meters per minute at a feed of 0.12 mm/rev. For narrower inserts, such as 2mm, 0.08 inches, and 1mm, 0.04 inches, tool configurations like QD26 and QD21 maintain efficient performance with reduced feeds of 0.09 and 0.06 mm/rev, respectively. A 1.5 mm, 0.06 inches insert used with QD21 achieves 0.07 mm/rev. Across all configurations, the Corot QD system provides consistent, precise machining results, ideal for deep grooving and parting off operations while maximizing material savings and surface finish quality. Nestled in Italy's Abruzzo region, Honda Italia's Atessa factory is a pinnacle of modern manufacturing, blending Industry 4.0 technologies, meticulous craftsmanship, and a relentless pursuit of quality. This sprawling facility produces scooters and motorcycles that embody Honda's global reputation for excellence. From die casting to final inspection, every stage of production is optimized to ensure precision, durability, and performance. Central to this process is the integration of high-performance tires, alongside sophisticated techniques in welding, machining, painting, and assembly. Let's delve into the intricate journey of how a Honda motorcycle is crafted at Atessa, with a spotlight on tire production and the factory's innovative processes. The production begins with die casting, a high-cycle process that forms the structural backbone of Honda's scooters. Two Buehler machines with capacities of 840 and 1,050 tons inject molten aluminum alloys into precision-engineered steel molds. This state-of-the-art technology ensures each component, from small brackets to large frame sections, is cast with exceptional accuracy. Every mold is monitored in real time, and traceability systems track each part's journey, guaranteeing consistency. Post-casting, components are cleaned, deburred, and inspected before advancing to the machining department. Here, numerically controlled machines from world-leading manufacturers execute drilling, boring, tapping, turning, and grinding with millesimal precision. Advanced measurement tools, including laser scanners and coordinate measuring machines, verify tolerances while skilled technicians oversee operations to ensure total reliability. Tire production, though typically outsourced to specialized suppliers, is a critical element of the Atessa workflow. The process starts with compounding, where natural and synthetic rubber, carbon black, silica, and chemical additives are blended to create a rubber formula tailored for grip, durability, and heat resistance. This mixture is extruded into continuous strips, shaped into tread patterns, and layered with steel or fabric belts to reinforce the tire's structure. Sidewalls are added to provide flexibility, and the green tire is molded and cured under high pressure and temperature, locking in the tread design and hardening the rubber. Upon delivery to Atessa, tires undergo rigorous inspections for defects, balance, and compliance with Honda's stringent standards. During assembly, tires are mounted onto precision-machined alloy or steel wheels, balanced to eliminate vibrations, and fitted to the chassis with torque-controlled tools to ensure perfect alignment and safety. In the Welding Department, robotic automation and human expertise converge to create robust, precise joints. Frames are welded using metal active gas mag techniques, which provide strong, consistent bonds. Fuel tanks require a more complex approach, combining mag, resistance welding, and braze welding to ensure leak-proof integrity. Highly trained welders program robots, monitor weld quality, and perform manual inspections using ultrasonic and visual checks. Post-welding, frames undergo mechanical machining to refine surfaces and are calibrated to exact specifications before advancing to cataphoresis, a corrosion-resistant coating process. The painting section comprises 3 specialized subsections: ABS, SPC, and CED. The ABS subsection applies vibrant, evenly spread paint to plastic fairings, achieving a high aesthetic finish. The SPC subsection optimizes paint application on steel components, reducing waste while ensuring coverage. The CED subsection uses electrodeposition to deposit a uniform, corrosion-resistant coating on metal parts. Skilled painters prepare surfaces manually for specific colors, ensuring flawless finishes and conducting initial quality checks. This blend of automation and craftsmanship results in a visually stunning and durable product. The assembly line is where components, including tires, converge to form a complete motorcycle. Designed for flexibility, the line adapts to new models through a lean production philosophy. Ergonomic workstations, equipped with modular trolleys, streamline material access, while A-class torque spanners ensure precise fastening of bolts and nuts. Assembly data is digitized, enabling real-time monitoring and traceability. Tires, now mounted on wheels, are fitted to the chassis, with alignment checks ensuring optimal handling. The line produces several hundred units daily, each crafted with operator safety and efficiency in mind. In the final inspection, every motorcycle undergoes dynamic testing on benches to simulate riding conditions, assessing engine performance, braking, and tire grip. Static visual inspections verify aesthetics and component alignment. Sample units are subjected to additional tests, such as stress analysis, to confirm compliance with design parameters. Only after passing these rigorous checks are scooters shipped to dealers worldwide. Honda Italia's Atessa factory exemplifies innovation and precision. From die casting and tire integration to welding, painting, and assembly, each process reflects Honda's commitment to quality, delivering motorcycles that inspire trust and exhilaration on every ride. The retreading process at Radberg begins with a meticulous selection of used tires, sourced through an international collection network. Each casing is visually and manually inspected by trained specialists to detect surface defects, structural fatigue, or sidewall damage. Only premium brand tires that pass these stringent inspections are approved for retreading. The selected tires then undergo shearography and pressure testing to detect internal separations, belt shifts, or trapped air pockets. Following approval, the casing enters the initial preparation phase, where it is buffed on precision-controlled machines. These machines remove the worn tread to a uniform profile, exposing the clean underlying structure and creating the optimal surface texture for bonding. After buffing, the casings are subjected to the skiding process to manually remove embedded debris or damage in specific areas. Repair patches or filler rubber are then applied and cured to restore casing integrity. Next, the rebuilding phase begins. Depending on the retreading method hot, either pre-cured treads are applied using specialized bonding cement, or unvulcanized rubber is extruded onto the casing to form a new tread pattern. The tires are then enveloped and placed inside autoclaves for curing. Under precisely controlled temperature and pressure conditions, vulcanization occurs, permanently bonding the new tread to the casing. During curing, temperature, time, and pressure parameters are continuously monitored by automated control systems to ensure consistent quality across batches. Post-curing, the tires undergo a series of quality assurance checks including balance testing, uniformity measurement, inflation pressure testing, and final shearography. The painting process of the China Airlines Boeing 777-300ER was a complex and highly detailed procedure carried out at Boeing's facility in Seattle. After assembly, the aircraft was moved into a dedicated paint hangar where the exterior surface was first cleaned and sanded to remove contaminants. A primer layer was applied to ensure maximum adhesion and corrosion protection. Next, technicians applied multiple base coats using high-precision spray systems. The fuselage received Boeing's iconic blue and white gradient, requiring careful blending of shades to achieve a smooth transition. The tail section featured China Airlines' signature red plum blossom design, painted in delicate layers to create a soft yet vibrant appearance. This required extensive masking and stencil work to capture the flower's fine detail and color depth. To ensure quality and uniformity, temperature and humidity were strictly controlled inside the hangar. Between each coat, drying and curing times were closely monitored. After all paint layers were completed, a clear gloss topcoat was applied to protect the livery from UV rays, weather, and erosion during flight. The entire painting process took several days and involved a team of highly skilled professionals. The result was a stunning and symbolic livery celebrating the partnership between China Airlines and Boeing. The cold forming of a saddle-shaped panel on a Neyland shipbuilding press involves a two-step process. First, the operator uses standard bending tools to form the panel into a basic cylindrical shape. This step ensures the initial curvature required for the saddle geometry. Once the cylindrical form is achieved, the operator removes the bending tools and switches to a press equipped with a rolling unit. This can be done by moving to another press that already has the rolling unit mounted. or by installing the rolling unit on the same press, which takes approximately 20 minutes. Next, the operator proceeds with the rolling phase to elongate and stretch the longitudinal sides of the panel. This step is crucial because saddle panels, also known as side stretch panels, require extended sides to match their unique three-dimensional contour. The rolling tools apply controlled pressure along the sides of the panel, gradually stretching the material to achieve the desired saddle shape. Throughout the rolling process, the operator continuously checks the panel against physical templates to ensure dimensional accuracy. Adjustments are made as necessary to match the required curvature and overall shape. This method allows for high-precision cold forming without the need for heating the metal. By combining bending and controlled rolling, the Neyland press effectively produces saddle-shaped panels that meet shipbuilding standards for form and strength. The result is a panel with symmetrical, elongated sides ideal for use in the hull or deck structures of ships. The Mr. T electric motor recycling machine efficiently recovers copper from motor stators. It cuts the stator in half, then pulls out copper coils using a hydraulic system. Suitable for 8 to 30 centimeter stators, it ensures 100% copper separation, low energy use, and high efficiency with easy semi-automatic operation. A ship suffered an unexpected breakdown while in canal waters. EC Repairs swiftly performed emergency steel repairs on MV Mariner in canal waters, including cropping and renewing sections of the transom plate and sideshell plating. The large-scale engine repair process begins with the dismantling of cylinder covers and the lifting of pistons as part of a crankshaft replacement procedure. Given the significant weight of these components, proper handling is essential. Specialized lifting equipment is used to safely remove each cylinder cover and extract the pistons vertically. Due to the potential for swaying during the lift, careful control is required. The use of hydraulic nut tools must be precise and in accordance with safety protocols to prevent accidents and ensure mechanical integrity. This initial step sets the foundation for the crankshaft replacement operation. Scrap loading, arc furnace smelting, continuous casting, billet making, hot rolling, cutting, inspection, and packaging. MedSteel specializes in producing advanced quality steel. A Seni excavator is produced through precision engineering, starting with CAD design, followed by steel cutting, robotic welding, machining of components, assembly of hydraulic and electrical systems, rigorous quality control, painting, and final testing to ensure durability, performance, and compliance with global construction standards. Crossmuller provides end-to-end structural fabrication services, including plate processing, CNC drilling, robotic plasma cutting, precision fabrication, industrial welding, and protective painting. Plate materials are processed and drilled using high-accuracy CNC systems to meet structural tolerances. Robotic plasma cutting allows for automated, repeatable profiling of steel components with high thermal efficiency and edge quality. Welding operations utilize certified MIG, TIG, and arc welding procedures compliant with structural codes and project specifications. Welded assemblies are subject to non-destructive testing to ensure joint integrity and structural performance. Surface protection is achieved through controlled painting processes, applying corrosion-resistant industrial coatings to extend product lifecycle in demanding environments. This integrated fabrication workflow supports heavy industry, construction, and utility sectors with reliable, standards-compliant structural assemblies. The world's largest crane vessel installed Equinor's Peregrino C platform, handling the horizontal top section and the second roll-up bottom part, row 1. The offshore installation spanned 2 to 2.5 weeks, involving precise lifts of massive components. Following the installation, piling operations commenced to secure the platform foundation. The project utilized giant lifting slings capable of handling loads exceeding 24,000 tons, ensuring safe and efficient operations. This complex offshore assembly demonstrates advanced heavy lift engineering and careful coordination to meet stringent safety and performance standards essential for Equinor's infrastructure development. The installation of a large-scale wind turbine requires detailed planning and precise engineering. Components such as the tower, nacelle, and rotor blades are transported to the site using cranes and specialized equipment. Heavy lifting machinery carefully assembles each part, with blades positioned according to wind direction. All connections are secured, following strict safety standards. After electrical hookups, the turbine undergoes system testing to ensure operational efficiency. The project is executed meticulously to maximize energy output and ensure long-term performance. Environmental and operational risks are minimized throughout the installation process to guarantee safety and reliability. Ahola Special handled a wide and long transport measuring 49 meters in length, 7 meters in width, and 6.85 meters in height. This oversized load required specialized routing, escort coordination, and precise handling for safe, efficient delivery. In rural aluminum pot casting, stone molds play a crucial role in the production process. First, high-quality stone is shaped into molds with smooth surfaces and heat resistance according to design specifications. Aluminum alloy is then melted in a furnace to the appropriate temperature and quickly poured into the stone mold for casting. The molten aluminum cools and solidifies within the mold, forming the basic shape of the pot. After cooling, the pot is removed from the mold and undergoes grinding and polishing for surface finishing. Finally, quality inspections ensure defect-free products. The use of stone molds enhances molding precision and surface quality, making it a vital step in rural aluminum pot manufacturing. Drescher Automation delivers a fully integrated transfer press system with coil feeding line designed for high-volume seat rail production. The line incorporates a robust straightening unit capable of processing high-tensile steel, ensuring accurate material flattening and feed consistency throughout the press operation. A Siemens Simotion-based control architecture governs all automation sequences, enabling real-time synchronization between decoiling, feeding, press forming, and transfer mechanisms. The system supports rapid die change procedures, aided by modular tool interfaces, and manually operated transfer rail couplings. These features provide operational flexibility and reduce downtime during product transitions. Coil changes are facilitated using inching mode, granting precise movement control during coil threading and alignment, enhancing both operator safety and setup accuracy. In production mode, the line operates continuously and autonomously, maintaining consistent cycle times and part quality. All functional units, coil handling, straightening, servo feeder, and press are electronically linked via the centralized control system for coordinated performance and error-free operation. Additionally, Drayer Automation oversees complete project management for such installations, ensuring seamless integration of mechanical components, automation technology, and control infrastructure. This end-to-end approach covers design, engineering, assembly, commissioning, and operator training, tailored to meet specific customer production requirements. The result is a highly efficient and scalable solution for precision seat rail manufacturing, combining mechanical durability with intelligent process control.